Hello everybody, welcome to my talk entitled Developing Neurocognitive Models of Joint EEG and Behavioral Data During Perceptual Decision Making. My name is Michael. I'm currently at the University of Amsterdam. This is a pre-recorded talk for the Neuromatch 4 conference. So in general, behavior can reveal cognition during decision making, and this is because we've developed mathematical models in mathematical psychology that have cognitive parameters that describe response times and choices. So if we have response time distribution for choice A and a response time distribution for choice B, then we can say something about the cognitive process. So for instance, when a stimulus appears and we have to differentiate the spatial frequency of our high or low Gabor embedded in noise, and we observe one trial response time for that particular experimental trial, then we can separate out non-decision time from decision time in that particular response time. Also, we can say something about the evidence accumulation process during an experimental trial when we accumulate evidence for choice A by reaching a top boundary or a specific amount of evidence, and make the choice for choice B when we reach the bottom boundary or a specific amount of evidence for choice B. So that would, in this particular example, would be a higher or low spatial frequency. Now, when we have EEG, we can say even more about this cognitive process. We can say that the N200 latency has been shown to encode visual encoding time, or the onset of decision making. So therefore, we can split non-decision time into visual encoding time and motor execution time. So this shows that joint modeling of human EEG and behavior reveals even more about cognition during decision making. Now we can say even more about the evidence accumulation process itself on single trials when we have correlates in the EEG of the evidence accumulation process. This has previously been shown by O'Connell and other scientists in the central parietal positivity slope. That's another event-related potential in EEG. And we have shown that the readiness potential encodes decision times and likely reflects more information about visual evidence accumulation and motor evidence accumulation. Now, in general, my previous work has been to develop directional models in which EEG measures describe cognitive parameters, which in turn describe human behavior. What I'm more interested in now is combining cognitive modeling with computational modeling, where we have integrative parameters that describe both behavior and EEG. So one example of an integrative model is a simplistic integrative model of choice response times and CPP slope. So if we observe choices and response times on single trials T for every participant, and these come from a drift diffusion model with drift rate, boundary, non-decision time, and the start point parameter for every participant P. But we also say that the CPP slope on single trials comes from a normal distribution with mean drift rate for every participant. Then we can both predict both observed EEG on single trials and observed choices. And so if we were to test this model against data, we could verify the theory directly. Now you can look at this particular simplistic example yourself at the GitHub page that I've listed here. I've also done work to extend this model, for instance, and others have done this work to extend this particular model to scenarios where the CPP is generated by a linear combination of drift rates. I've also done work to show that when we have the addition of other EEG measures, we can say even more about the cognitive process, and I'll provide a link to a talk in the links below. So this particular simplistic model does recover parameters, and you can run it yourself. So you can see and look at a particular integrated model, at least one example of an integrated model. On here, the x-axis here, we have the simulated parameters, and on the y-axis, we have the posterior distributions when fitting this in a hierarchical Bayesian model, with the stars and the circles being the mean and mode, respectively. And the other blue lines reflecting the 95% credible intervals, and the teal lines representing the 99 credible intervals. So in general, we do recover the data, besides some extreme examples where we're unsure of the parameters. Okay, so in general, testing these neurocognitive models against data are absolutely necessary for understanding neurocognition and for testing neurocognition. So it's my job to develop these models before testing them against data. I'd like to thank my previous collaborators, Ramesh Srinivasan, Joachim van der Kerkhove, Kitty, Mariel, Steve, Aishwarya, Jessica, all at the University of California, Irvine, or at some point was at the University of California. I'd also like to thank the University of Amsterdam for support of my current work, as well as the National Science Foundation for support of this work. Thank you so much for listening to my talk, and enjoy Neuromatch.